Okay, we're going to talk about line integrals involving just dx, dy, or dz. So previously we talked about line integrals where we had the dot product of a force or of some vector field with dr, where dr meant dx, dy, dz. Now, what if you have just one of those d's? So let's say the integral over c, for example, of x e to the y dx, where c is now given by some curve. What does this mean? Well, it actually just means dx is just x prime of t dt. Again, we just used the cancellation of the differentials. So remember that dr, it actually just meant before it was the velocity times the change in time. That gives you the change in displacement. Now, as it turns out, you can just do something similar with this dx. And then you just proceed to integrate t as normal. So let's do a simple example of this. Let's evaluate x, y times the square root of z dz. We'll just use the square root of z to make the integral a little nicer. Where c is now given by x equals t, y equals t, and z equals t squared. So according to this recipe, dz, it'll just be equal to dz dt times dt. So it's just 2t times dt. And similarly, square root of z will be equal to t. So, oh, and I'm sorry, the curve has limits 0 to 1. So if we just plug in t, then our integral over c becomes t equals 0, t equals 1, and then finally x is t, y is t, and z is t. Oh, I'm sorry. Y is t, and z is t, and dz is 2t dt. So our integral is just 0 to 1 of 2 times t to the 4th dt. So we should get 2 over 5th. Okay, so again, with line integrals, they're always just one-dimensional, so ordinary calculus works. To see a slightly more complicated example of parameterization of one of these things, let's try x e to the y dx, where now c is given by the curve x equals e to the y from 1, 0 to e comma 1. Okay, so the curve is not given in t, it's in terms of x and y, so I like to just plot some of these things whenever it's not clear what's going on. So x, y, and I want to plot it as a graph, so I'm going to solve for y. So y is just the logarithm of x, so we kind of know what that looks like. And you could also just think of this as e to the y and plot that and then flip it. So here's our point 1, 0, and then over here, if this is e, here will be our point e1, y equals 1 here. So that means the portion that we're interested in is this red portion. And so we start at 1, 0, and then we end at e1. Okay, so where's the t? So now we're going to introduce t. And so you just make x of t and y of t solve x equals e to the y in a good way. So for example, y equals t, then in order for the equation to work, then we need x to be equal to e to the t. So therefore, if our choice of parameterization, which is always arbitrary, but as long as it solves that equation, we're good. So this choice of parameterization, it works. Okay? And so now what we need to do is we need dx, and we also need the limits. So dx is easy because it's just dx dt times dt, because we want everything in terms of t. So it's just e to the t dt. Okay, now the limits, t start, again it's y, right? Because that was our nice choice that we used. And y is 0 at the starting point. Okay? And t end, again, it's just y. And so now if we look at the end, y is 1. So that's what we use for t. So therefore, the integral over c of x e to the y dx, we just get 0 to 1. Those are our t's. And x is just e to the t. And e to the t is also our y. This is really e to the y. And then finally, e to the t dt, that is our dx. So our integral is simply e to the 3t dt, so it's 1/3 e to the 3 minus 1 if you integrate that thing. And so again, the hardest part is just setting up what this line integral means. And once you do that, now it's just 1D calculus. Okay, thanks for watching.